plus V2 times RF divided by R2 plus V3 times RF divided by R3. Okay, so this shows that the output voltage is basically a linear combination of the input voltages. Okay, and all of these coefficients are positive because these are resistors, right? So again, if you choose R1, R2, and R3, R1, R2, R3, and RF to be the same, what you end up with is output voltage is equal to negative of V1 plus V2 plus V3. Okay, so here, look at this. Because our three voltages are connected to the inverting pin, our output voltage becomes has a reverse polarity as our input voltages. So if you want to make this positive, you can use an inverting amplifier, right, with the coefficient of 1 to make this positive, right? So like, let's say, like if I add inverting amplifier like this here, that this is grounded, negative, positive, if these two are the same, this voltage VO1, VO2. VO2 is negative of VO1. So you can cancel this one if you cascade this somewhere with a inverting amplifier with the coefficient of 1, or actually negative 1. Okay, so, but that wasn't what I wanted to discuss right now. But this is our output voltage. This circuit is adder, so we can add any number of input voltages here. So like if you had like 4 inputs and you wanted to add them, or 5 inputs or 2 inputs, you can just basically increase the numbers by adding more resistors here connected to your input ports. So far we've done a review of op-amp, and we saw 4 different circuits that you saw previously in your previous courses: inverting amplifier, non-inverting amplifier, subtractor, and adder. Now I'm gonna introduce 2 new circuits that you might have not seen before. I'm not sure if you saw this before in your other courses, but I just assume that you haven't seen this before. Again, we are gonna have a negative feedback. So the first one, again, this is grounded. Let's have our input voltage. Let's go to a resistor, and here in the feedback I have a capacitor. Okay, so again we have a virtual ground here. Okay, it's not physically connected to ground, but because op-amp makes sure that these 2 voltages are the same, this voltage is almost 0. Okay, and here we have R and C. Okay, now I'm gonna do this circuit analysis in S domain. Okay, or actually let me do this in the frequency domain. If you want to do this in the frequency domain, the impedance of the resistor is the same as the resistor. What is the impedance of a capacitor? XC or ZC, it's 1 over, I'm just gonna write J omega C, right? You've seen this before. If I want to do this in the S domain, you remember that we can replace J omega with S, so it becomes 1 over SC. Okay, now let's write KCL at this node. Again, this current, it's gonna be exactly the same as this current. So let's write that. V in minus 0 divided by R, it's equal to, so this was the Ohm's law for the resistor, it's equal to 0 minus V out divided by XC, right? So I'm just gonna simplify this now. So it means that VO, it's equal to negative XC divided by R. So I'm taking this one out, this one the other side, times V in. Now let's just replace XC with 1 over SC. So it means that V out is equal to negative, am I making a mistake? Let me just double check this one. V in minus 0 divided by R is equal to 0 minus V out divided by XC. V out divided by XC is equal to negative V in divided by R. I multiply everything by XC, that's correct. And XC is 1 over SC. So this becomes negative of RC. Let me actually write this like this, times V in divided by S. Okay? So this is like how the output voltage and input voltage gets related, but this is in the frequency domain or S domain. Okay, now you guys remember that if you, this is basically VO in the S domain and V in the S domain. Now you guys remember that 1 over S times a signal in the S domain, what does that mean in the time domain? You're right, it means integral, right? So it means that VO of t, it's gonna be negative of 1 over RC integral of 0 to t of V in, let me call it theta. Integral of the voltage, it doesn't matter like what this is, like this symbol technically doesn't have to be this one, it shouldn't be this one, so it just like this is like the variable of the integration. We basically take an integral of the input voltage over time, and so this circuit, it's actually called, can you guess what it's called? Integrator. Okay, so with this one, again, if you choose the values of R and C carefully, you can, this is going to be a coefficient for your integral, right? And you just like basically this circuit takes the integral of the input and you have it in the output. So this is called integrator.